Now recall from single variable calculus that if you want to determine the area underneath a function between two values, the idea is to approximate the area using rectangles. So what you need to begin with is what's called a partition. Now in the partition, you take the interval a to b and you subdivide it into n equally spaced subintervals. Now this requires a set of points. So this first location is x0. Come up with a second location x1 and then x2. Each of these is separated by the same width. Now you don't technically have to use the same width, but just to keep things simple, we'll keep them all equal. You pick some sample point somewhere in that subinterval and you build a rectangle based on where that sample point intersects your function. So if you do this for all the subintervals, the area underneath the curve gets approximated by the areas of these individual rectangles. The height of the first rectangle is f of x1 star times delta x. Now here is this x1 star. It's called the sample point on that first interval. Then you've got the second rectangle, height times width, and there's the x2 star. So on and so forth until you get to the very final one of these rectangles. Now this can be written in sigma notation or summation notation, and here we've got some xi star times delta x. Now this type of expression here is called a Riemann sum. If we want to define the area, what we'll do is take more and more of these rectangles and make them thinner and thinner and thinner. And if we continue to refine the rectangles in this way and we come up with an answer, if we come up with a number, that number is what we define as the area. So this is the definition if this limit exists. Now remember that here we are interested in the function being a positive function on our subinterval. So what this did is it led mathematicians to define the definite integral. So the definite integral is defined according to this calculation involving the limit of a Riemann sum. In the special case that your function is positive, the result of the definite integral will represent area, but generally the definite integral doesn't necessarily connect to area. When does the definite integral exist? When is f integrable? This is the phrase that we use. So there are several sufficient conditions that we can talk about. Sufficient means these conditions will do the job of making sure that the function is integrable. So if the function f is continuous on AB, this limit will exist and the function will have an integral. Now the other condition here is if your function is piecewise continuous on your interval AB. Piecewise continuous is something a little weaker or a little less well-behaved than continuity. Piecewise continuity means that your function is bounded on the interval AB, which means that the size of your function less than or equal to some positive number, and f has a finite number of points of discontinuity. So that means breaks or holes or gaps, etc. So for example, functions that do something like this can be integrable on your particular interval. Knowing whether a function is integrable just means that you know that this definite integral will exist. But a more important question is how do we actually calculate this definite integral? Other than very, very simple cases, it's almost impossible to use Riemann sums. We're saved by the fundamental theorem of calculus. Now, the fundamental theorem of calculus says if your function f is continuous on this interval AB, then the value of this definite integral can be very simply computed by taking the difference in the antiderivative of the function. So the antiderivative is a new function that's related to your original function in this way. If the value of your function is greater than 0, then the definite integral calculates the area, and otherwise, this is going to produce what's called the net area, or sometimes it's called the signed area, which just means add up all the areas that are above and below, and you could end up with a positive or negative number. What we want to do now is extend the concept of integration to multivariable functions. And we are going to focus on the case of a function of two variables to begin with. To motivate this, geometrically what this is saying is if our function is greater than or equal to 0 over some rectangle in the xy plane, what is the volume under the function and above this rectangle? And we'll call the rectangle R. Now, to try to illustrate this to you, here's the idea. As always, here is our usual 3D coordinate system. We are going to have some sort of rectangle that lies in this xy plane. And we're going to define this rectangle as all the points that satisfy x is between a and b and y is between c and d. So we're going to give this a new notation. This is going to be something called a Cartesian product, where it says all the possible points in this first set combined with all of the possible points in this second set, and we're going to list them as xy pairs. Here's our function. What we're trying to do is figure out the volume underneath that function, but above the rectangle. Now, as before, what we're going to try to do is use this subdivision idea. So what we're going to do is partition this rectangle R into equally spaced rectangles. So we'll draw our usual xy axes here, and we'll take our rectangle. So its limits here will be from A to B, and then from C to D. And what we're going to do is partition everything as before. So we'll have an x0, x1, all the way down to xn. xi will just be A plus I delta x. Delta x will just be B minus A over n. And similarly, we're going to make a partition in the y direction. Just for simplicity, we're going to use the same number of points in x as we do in y. However, we are going to use a different index. We'll use the letter I for the index of x, and we'll use the letter j for the index of y. So these are our different grid points. And here is our y1 and our y2. You can see what will end up happening is we will make a grid of all of these rectangles here. Some arbitrary rectangle here is the rectangle Rij. Now we can think of this rectangle Rij as the Cartesian product between all the points between xi minus 1 and xi and yj minus 1 and yj. Now, in the images below, I'm going to try to show you the idea behind this subdivision concept. So on this picture down below, what we're trying to do is now calculate the volume above this rectangle Rij. So the volume then is dependent on the height, which is related to some sample point in that rectangle times the area of that rectangle on the bottom. We are going to write f of xi star, yj star, and we'll just call this delta A. The total volume is then a double sum, I equals 1 to n, j equals 1 to n of the volume in each one of these individual boxes. And essentially it's trying to add up the contribution of volume from each one of these columns that we see here on the right. The total volume then is approximately given by this double sum, f of xi star, yj star, delta A. And again, this is the approximate volume. You can see that in the picture on the left here, sometimes this column peaks over the function, sometimes it peaks below. So what we are going to do is define the volume as the limit as the number of these boxes goes to infinity of this double sum. This double sum is what's called a Riemann sum, but it's just been extended to a function of more than one variable. If this limit exists, then the volume will exist. Now, we'll also need the function to be positive in general, and what we then do is also define something called a double integral. It's going to be an integral over this rectangle R, f of x and y dA, and it will be the limit of this double Riemann sum. if this limit exists. If the limit exists, we will say that f is integrable on R. When is a function integrable over that rectangle? So just like before, it's sufficient if the function is continuous over R. As before, if the function is piecewise continuous on R, then we will be integrable. So now what does it mean to be piecewise continuous? F has to be bounded, which means the value of the function less than or equal to some positive number, and where the points where f is discontinuous consists of a finite number of points and or continuous curves of discontinuity. That means you can have functions with jumps in discontinuity, kind of like this. There's a finite curve of discontinuity. You could have a function with a hole or several finitely many holes. You could have a function where a portion is cut out, just like this. And this would be a curve of discontinuity. So as long as it's got finite number of these curves, the integral will exist. As before, evaluating double integrals is hard using the Riemann sum definition. You can approximate it with certain techniques. So for example, you could use the midpoint method or Simpson's method, or you can get exact values if your function is easy. So for example, if I asked you to evaluate this particular double integral where your rectangle is defined as all the points on this Cartesian product, what this is saying is you've essentially got the xy plane, you've got some rectangle, and you've got a function that's a constant. And you're trying to build this solid above the rectangle but underneath the function, and you would like to figure out its volume. It would just be the height times the area of that bottom face. Well, we know that the height of this function is 5, and the area of the bottom face is simply just going to be 2 minus negative 2, 3 minus 0. 5 times 4 times 3, which is 60. So all we're doing is calculating the volume of a box. You can extend it a little further, so let's calculate the double integral of this expression, where R is now a rectangular region defined like this. What we've got is essentially a triangular prism. We've got a function that's defined in this way, and the volume of this expression here would simply be the area of this triangular face times this depth. Well, you can see here that if this is x and this is y, the depth is simply going to be related to the y values here. There's the 3. So this value would be 3. The area of any triangular face is 1/2 the base times the height. Well, we know that for this function right here, it has to have a height of 1. The base is just going to be equal to 2. It's the difference in those two values. So the volume in this particular case is going to be 1/2, 2 times 1 times 3, which just ends up giving us a 3. So in these simple cases when we can use geometric arguments, double integrals are easy to calculate. In the next video, we'll talk about a way to directly calculate these integrals, but for now, we'll just simply state property of some of these double integrals. And we won't give any proofs related to these properties, but they're all very similar to how they're derived in Calculus 2. So we are going to assume that the functions we have, f and g, are integrable on R. If we are simply integrating the function 1, this will just produce the area of R. We've got our usual linearity. So if we have the sum of two functions, it's simply going to be the sum of their integrals. If we are double integrating function times constant, so if it's being scaled, it's simply going to be the scale of the integral. We've got this what's called monotonicity property. If one function less than or equal to that other function on R, the integral of the smaller one will also then be less than the integral of the larger one over that same rectangle. And finally, we have this absolute value property that the absolute value of the integral is less than or equal to the integral of the absolute value of the function over that R. And finally, if R is a disjoint union of rectangles, R would just be R1 union with R2 all the way down to union with some Rn, meaning we've just got a bunch of rectangles that don't overlap like this. Then the integral of a function over that is simply just going to be the sum of all of those individual rectangles for each rectangle Ri.